Welcome to the second part of 7th lecture. So, we have learned how to find maximum matching in bipartite graph using augmenting path algorithm, and the stopping criteria for the augmenting path algorithm is that if there is no augmenting path with respect to the current matching, then you stop there, okay, and you return that matching as the maximum matching. So, we will prove a theorem now which says that a matching is maximum if and only if there is no augmenting path with respect to that matching. This theorem proves the correctness of the augmenting path algorithm. So, let me state the theorem now. So, this is due to Burge 1957. A matching is maximum if and only if there is no augmenting paths with respect to M. This proves the correctness of the augmenting path algorithm. So, we will prove this part that you are given that the matching M is maximum. So, both are by contradiction. So, this part is by contradiction. So, what it says is that given that M is a maximum matching, okay, for the sake of contradiction, suppose there is an augmenting path P with respect to M. Since there is an augmenting path with respect to M, you can improve your matching. You get another matching M prime, which is the symmetric difference of your matching M and the augmenting path P, and then we know that once we augment or once we take symmetric difference of the current matching and augmenting path with respect to that matching, the matching size increases by 1. So, the matching size or size of the matching M prime is equal to size of the matching M plus 1, right. So, this contradict the maximality of M. So, we started with the, it is given that M is a maximum matching, but you are getting a matching which is of bigger size than the maximum matching. So, that is a contradiction. That means there is no augmenting path with respect to M. Okay, this part is reasonably okay, and the other part is you are given that there is no augmenting path P with respect to M, and then you have to prove that the matching M is a maximum matching. Okay, so this part is also using contradiction. You have to prove that M is a maximum matching. So, you assume that suppose M is not maximum. M is not a maximum matching. Okay. Let there is a bigger matching, let M star be maximum matching, and of course, M star is maximum matching. So, the size of M star is greater than the size of M. Now, we use the previous theorem. So, I have two matchings M star and M star is a bigger matching. Now, I take the graph like F was the notation for the previous theorem. I take the graph which is the symmetric difference of these two matchings, M symmetric difference, M star symmetric difference M, and we know the property of this graph, right. And so, since M star is bigger, Q has more edges from M star than M. This is okay. Now, from the previous theorem, since Q is like symmetric difference of two matching, what we know is that every component of this graph Q is either a path or a cycle, right. So, every component of Q is either a path or an event cycle or an event cycle. This is the theorem or result that we proved just now, and also we note that this is not only they are alternating cycles, right. So, the edges of every path and cycle in Q alternate between edges of M minus M star and M star minus M. So, now it is easy to understand all this statement, because we have just now observed all this thing using an example. Okay. So, now since this is a event cycle, every component of symmetric difference of m and m star is either an alternating path or an alternating event cycle. So, in the event cycle, the number of edges from m minus m star and the number of edges from m minus m star are the same. So, the only difference, but there are more edges from m star than m in the graph Q. So, then there must be a path, that is why there must be an alternating path with more edges from m star than m, and this path is an augmenting path, with respect to m, which is a contradiction. Because we have assumed that there is no augmenting path with respect to m, and then for the sake of, it is given that there is no augmenting path with respect to m, and then for the sake of contradiction we consider m is still not maximum matching, some other matching is maximum matching, and then finally we came to the point which says that there is an augmenting path with respect to m, which is contradiction to the first consideration that there is no augmenting path p with respect to m. So, that is the end of this proof. So, we have proved that a matching is maximum if and only if there is no augmenting path with respect to that matching, and that this theorem proves the correctness of the augmenting path algorithm. Well, so we have some time now. So, we will prove one problem which is not related to the maximum matching maybe. So, let me consider this problem. Every graph with delta g, if you can remember, this is the notation for the minimum degree of the graph g, minimum degree greater than or equal to 2 has a cycle of length at least delta g plus 1. It is a good problem. So, the minimum degree is given to be greater than or equal to 2, which is delta g, then there is a cycle of length delta g plus 1 in the graph g. So, how do you prove this? Okay. Well, so let V naught, V 1, V 2 up to V k be a maximum length path in G. Okay. So, here is the maximum length path B naught, B 1, B 2 and B k. Since this is a maximum length path, this proof is similar to a proof that we did in to prove that to prove a result in trees, that every tree with n vertices has at least n greater than or equal to 2 has at least 2 leaves. Okay. Well, so since this is a maximum length path, I can claim that all neighbors of B k lie on the path. Say let me call this path as P on the path P. Okay. This is true because if there is a neighbor of V k which is not here, you can list that vertex here and get a larger length path, right. So, that is why since this is the maximum length path, all the neighbors of V k are here. So, of course, this is a neighbor of V k and the other neighbors are also in this path. Okay. Well, okay, let me call it, this is V 1, this is V I plus 1. Okay. So, if I is less than k and I is the minimum index with V I V k belongs to E. That means, this is the minimum index vertex in this arrangement, which is a neighbor of V k. Then what you can do is that you get a cycle. This is a cycle, you form a cycle, right. This is the largest cycle that you can construct here, and what is the length of this cycle. So, V I plus 1, V k and then again V I is a cycle of length at least delta G plus 1. This is not difficult to observe. If all the neighbors are consecutive, you will get a cycle of length exactly delta G plus 1, because delta G is the number of neighbors, the minimum number of neighbors that the vertex V k has. So, this is a cycle of length delta G plus 1. So, we have proved that every graph with minimum degree delta G has a cycle of length at least delta G plus 1. So, today we have learned how to find maximum matching in bipartite graph using augmenting path algorithm, and in the next lecture we will learn more properties of related to matching both in bipartite graph and matching in general graphs also. Thank you very much.